Good morning. Today, I'd like to continue talking about the flux of dust en route to making the discussion relativistic. Right now, we're still going to assume that we're in a Newtonian situation. We will use Cartesian coordinates for space and the absolute time as time. Previously, we saw that the number flux of particles across a plane was the number density, n, times the dot product of the velocity vector and a unit normal vector to the plane. Each particle is going to have the same amount, capital A, of some quantity. This quantity might be charge, mass, components of momentum in various directions, or some other quantity. For example, each particle might have the same mass, m. The flux of mass across the surface will be the amount of mass times the flux of particles across the surface. M, number density, velocity vector, dot product with unit normal vector. Of course, the mass of individual particles multiplied by the number density of them is the mass density, rho. The flux of mass across a surface of constant x is the mass density times the speed in the x direction, with similar comments holding for the flux of mass across surfaces of constant y and of constant z. We figured out using the L by L cube argument that if mass is conserved, then this differential equation must be true. It's interesting to note that the time quantity apparently is being treated somewhat differently from the spatial quantities. From what we know of relativity, this can't stand. We will have to do something about this, but not now. We could, but are not going to, repeat this entire argument for any quantity that the particles carry. For example, each particle carries a certain amount of momentum in the x direction and an amount of momentum in the y direction and an amount of momentum in the z direction. For example, the flux of the x component of momentum across a surface of constant x value is the number density times the amount of x momentum that each particle carries times the dot product of v and, in this case, I, since we're looking at a surface of constant x. V dot I, though, is just the x component of the velocity vector. This is n times m times vx squared. That is to say, it's the mass density times vx squared. The flux of y momentum across a surface of constant x is the number density times the amount of momentum in the y direction that each particle carries times the velocity vector dot product the normal vector. In this case, this reduces to the mass density times v sub y times v sub x. Following the same procedure, the flux of the z component of momentum across surfaces of constant x in the end reduces to the mass density times the speed in the z direction times the speed in the x direction. You can do exactly similar calculations for the flux of various momentum components across surfaces of constant y, and also for surfaces of constant z. The details should be fairly clear, so I'm just going to present the results of doing that. There is an interesting pattern to this. Each one of these 9 fluxes is the mass density times the product of 2 velocity components. Moreover, the flux of x momentum across a surface of constant y and the flux of y momentum across a surface of constant x are the same. This number and that number are the same. This number and that number are the same. If I were to arrange all of these fluxes into a matrix ordered in this same way, that matrix would be a real symmetric matrix. And we know from linear algebra many facts about that kind of thing. In fact, if I write this in matrix form, I'll notice that there's a factor of the mass density in each one of the elements of the matrix, so I could factor that out front. Also, if you know linear algebra, you'll recognize that the matrix that remains has a very special structure to it. If I think of V as being a column vector, V transpose will be a row vector, and this matrix will just be V times V transpose. In linear algebra, this is called the outer product of the two vectors, as opposed to the inner product, which would be V transpose V. If you remember, in our tensor development, we've also had something called the outer product. This is becoming very suggestive. To finish the description of all of these fluxes in some reasonable way, we still need to worry about how the time coordinate fits in to all of this. This outer product business points the way to what we should do, but we'll put that off until the next video. I hope everyone's having a good day, and I'll talk to you again soon.
There is nothing wrong with your television set. We will control the horizontal. We will control the vertical.